So I promised to do, or the organizers picked one of the talks that had war stories from .NET team. This is a talk I gave for the first time 2 weeks ago in Oslo. Actually, 2 days ago the video came out. Did anyone see it? Okay, well, you're gonna be bored a little bit, I apologize. So I have more stories, but originally it was like, I gave the talk at Netherlands as well, and in Prague already. And somewhere between 45-60 minutes based on that, but I have to talk fast. So hopefully, if somebody feels that it's too fast, raise your hand. I know that nobody will do that because everyone is shy, but I wouldn't mind, just like nudge your neighbor and maybe they will raise the hand for you, if that happens. But I'm gonna try to speed a little bit through that. So. Let's start. The agenda, what is it going to be? It's going to be stories. It's going to be about investigation on the .NET team, not only from me, but most of the stories actually I either lived through or kind of was manager on the team when it happened, or was nearby at least, through my 14 years on the team. And some of the lessons learned on the way that we kind of learned from those things. What's not on the agenda, so you will not see any source code, you will not see any debugger, and you don't need any deep knowledge about .NET, the things that actually I'm gonna, that are needed, I'm gonna explain. I'm gonna start with the fun. My first investigation. So it was actually in, so I joined like 2005 October, and in January we got, which means I've been 3 months in Microsoft. This fun thing kind of came through. So it was a build lab somewhere in Windows. So some Windows component was building, and once per week they got a crash, and it was actually access violation. So it popped a dialog, and you had to log in on the machine, you had to click because they didn't have anything that would kill it on its own. It was pain in the ass, when they got it, this kind of thing, the first thing they noticed that, hey, we have just recently updated .NET Framework 2.0, so this is 2006, this is not Core, yeah. This is .NET Framework, it didn't exist back then. It was called Survive, maybe. There was toolset, and they updated it to, the RTM, the final version of the 2.0. So the first thing, like, oh, it's your fault, right? Obviously, if you change something, it's your fault. So the good news is that they had a repro, which means that they were able to kind of, on that machine, when they kind of ran it over and over, once in 50 rounds roughly, they were able to hit the issue. Interesting thing that, how it happens, the first it was dialog, like, hey, we changed toolset, .NET team, your fault. So in .NET team, it was like, first it started with MS build, because they ran MS build. MS build didn't look at it like, oh, what do you do? Oh, you run the C# team, go. C# team look at that, like, can we get a call stack? Eventually, because we had the repro, they could get a call stack. They look at the call stack, hey, this is metadata. And that's how it got to me, because I was the brand new owner of metadata. Lucky winner. Interestingly, they ran it as well overnight, so there was like some, it was not 1 in 50, like, it would be 2%, but it was slightly less, but still, like, that crash, the crash was kind of repeatable. Once you have such repro, it's good. So we got a call stack. Before we look at the call stack, I will use some quotes, which I kind of liked when I kind of dig out the old emails. So the first one is basically, somebody looked at that and said, like, in the code stack, like, it looks like that, stack is a little bit corrupted, some boilerplate checking code, that's bad, and nobody raised a red flag. Now with all the experience, as soon as, like, somebody hears or says, like, hey, stack is corrupted, it's like, oh my gosh, right? This is a security issue. We have to do something about that. Back then it went silent. I don't know, probably nobody smart was there, or nobody noticed, or maybe the security was not that far progress back then. It was interesting. The other interesting thing that, when they found me, like the C# team found out, like, hey, metadata, that's Karel. They ping me on IM or something, and like, yeah, I kind of owned the code for 2 months or 3 months. I didn't do anything serious in it, so yeah, let's have fun. It might take some time. And here's the call stack. This is the only call stack you're gonna see, by the way. So it's a little bit modified. I removed the CPP files and things. If you look at that, it starts with the C# compiler. It's the old one, not the Roslyn, not the cool one, right? This is the C++ native thing. Bunch of calls, up to kind of defining some parameters in the reg meta, which is the class, and there's some destructor of the read-write block or whatnot, and that just like blew up, and eventually from the assembly, or it looked like it's something corrupted on the stack. So the question was like, who corrupts the stack? How can it happen, right? So what was the first thing that we thought? could be GC, right? GC tends to kind of go and patch up your things all over the stack, and then like, well, wait a sec, this is not managed code, right? This is C#, this is C++. GC is not in the picture, so that was a false, alarm. So we looked a little bit, or I looked a little bit deeper, and found out that actually there was like value change between caller and callee. It was one thing, and what was more interesting, it was like single bit flipped. I mean, it looked like, hey, single bit is different. Like, you have some value, you pass it somewhere, and suddenly, when it's again on the call stack, the bit is flipped. So you look at it and say, like, who corrupts that? Like, the first thing that comes to mind is like, could it be like GC card table? It's known to kind of say, like, hey, I have some region of memory, let's set the bit, that it's dirty, so GC goes through that, and then again, like, no. Of course not. Like, we are not Roslyn, didn't exist back then. This is C++. Again, like, there's no GC involved. But it was interesting to see, not only in my mind, but as well, like, when I discuss it with friends, the first thing, like, as soon as something magic happens, the first thing to blame is GC. Maoni knows a lot about that. It's wrong, but such is stuff. By the way, if you ever need to learn x86 assembly, I knew kind of x86 assembly, but always what it took me a while, like, where are the kind of the parameters, where are the locals, is it plus, minus, like, if you have investigation like this, which took like 3 days, you will learn a lot. So this is a great way how to learn that and do a really good deep dive. Anyway, so after all these kind of suspicions, we said, like, so could it be like hardware bug, right? That's weird. Like, why would it fail exactly on the same call stack? But maybe it could be. And guess what? When we asked the team, hey, does it by chance reproduce on only one machine, right? Is it hardware related? And so it was like, how did you know? So like, well, we had a hunch about the hardware. And then the next question was like, so why does it fail always on the same call stack if it's some hardware issue, like maybe memory or something? It was really weird, but such is life. It was a good question, no good answer, and honestly, it kind of looked like magic, but that's what it was. So the lesson learned, I learned from that, was first of all that debugging hardware issues is extremely costly and it's hard. You gotta learn x86 and everything along the way, or the machine things, and. The next actually key takeaway from that, which I'm really using until today, is like, the question, does it repro only on one machine? Because if it's only one machine problem, it's suspicious. Like, you might think twice, like, am I gonna really go deep into that? Am I gonna investigate? Because you might end up in something like hardware. Now, I would love to say, like, I'm so smart, I did one thing and immediately learned these lessons. It took me one more hardware issue to kind of learn these lessons really, but since then, honestly, if you see me ever on GitHub, and as soon as there's something suspicious, like it's like, oh, something is really funny, weird, my first question, and like I think that Victor can probably, even confirm that, is like, does it repro on one machine? Because if it does only one, I'm not talking to you, because that's, it's just waste of time. Like, it's a huge investment. I think the second one took me like 1 week or something like that. But it's great, it's cool. Like, you debug something like, hey, 1 bit flipped or something. Yeah, it's hardware error, and oh, where's my week? Gone. Interestingly, when I kind of talk with a couple of friends or a couple of coworkers on the team, there were two variants of the same story that I kind of liked. In one extreme case, actually, some people actually even asked for, like, is it the same type of machine? Because I think that once we actually had really some driver bugs that again, like, corrupted things exactly in the same place, somewhere in our code, and we got it over and over. And on if it was different hardware, different kind of hardware with different drivers, everything just worked fine. That was actually nasty to kind of track down as well. And then Maoni, who doesn't know, she's the guru, architect, and everything behind GC for the last at least 10 years. She had actually back like 10 years ago or something like that, 5 years ago at least. She had this kind of, when I told her this story, she's like, you know what? I have a different variant of that. I always ask people, does it reproduce on VM? Or on real hardware, because if it's VM only, I'm not looking at that. Because over time, because the .NET was used everywhere, early days of VMs and virtualization, there were bugs, in those drivers. There were like bits flipped and things, and GC doesn't like that. Usually kind of crashes somewhere, it's blamed, and then when you track it down that it's really the VM hardware or drivers below you, you basically say, like, what, I'm done investigating something on VMs. Obviously, the technology moved on, now it's very mature, and saying something does it reproduce on real hardware would not work in these days because everything is in the cloud, or most of the things, but it's kind of interesting spin on that. Another story, so this was about metadata, is about metadata. And first I'm going to give you some kind of background of the format of metadata so that you can appreciate the story. So first of all, metadata is basically, so what's metadata? You write your code, C# code. There's IL, you probably hope everyone knows that. That's the kind of the intermediate language. It's kind of the bytecode, like in Java or something like that. It's later translated into machine code or assembly, whatever that executes on the processor. And there's actually associated part of the file is like 20–30% of that is actually metadata. And metadata describes like, hey, you have these types, they inherit from these objects, they have these methods, and each method starts, the IL starts with an offset over here in the file and the type of stuff. So kind of the meta description of your program. And it's really a database in the sense that there are tables, because by the way, it was designed by people who did databases, so that might be telling. So there are kind of tables, and the tables have rows and they have columns, and there's example of the type definition table. So if you have a type, let's say type foo, you have information something like hey, it's public type, it has some namespace, it extends something. For the simplicity, I removed it. It has some method list, it has some parameters. Oh, sorry, parameters not. Properties, fields, and those type of things. Again, I kind of abbreviated over here a little bit. And there's an interesting part, and that's whenever you have kind of indexes into other tables, or for example the names. The names are not inserted in the database, right? There's a string heap somewhere on the side, which contains all the strings, and the type name basically just says like, oh, I'm type with the name which starts over here. So kind of like pointer, something like that. And because it was like designed with 20 years ago, or how old is .NET? Back then, like bytes mattered, and they matter again because of web and everything, right? So 2 bytes versus 4 bytes was a big deal. So basically, whenever something could be, there were like less than 64K of something, and it could be represented in 2 bytes. It was kind of indexed by 2 bytes. So whenever you open a file, at the beginning there's information about like oh, I have this many methods, this many types, this many strings, and that stuff. And based on that, you determine is 2 bytes enough to kind of index that or not. Simple, right? So what happens? And actually, sorry, I skipped thing. The thing I wanted to actually explain how the method list works. So the method list works like if you say like hey, the type foo has some methods, you basically say that the method list is the first index of the first method. And how do you find how many methods you should look at? You look at the next type, so at the bar, and say like when that type starts, right? So in this case, the type foo has method number 10. That's its type. Sorry, that's its method, and that's only one method because the method 11 already belongs to the next type. So it's kind of like continuous list, and you basically just say like where my kind of block of methods starts. Quite simple. Now imagine that you have no methods. That can happen. We have structs which have only fields and things. Then it would look like, for example, that if foo didn't have any method, then the bar would start as well as method 10. You would then look at the method foo and say like, hey, it's number 10, but the next one starts at number 10, which means, I have nothing. Nothing belongs to me. Simple. So what if it is the last type definition? What if the last type, and let's say it's the bar, has no methods? Then the method 11 cannot be existing, right? Because if it would be the existing one, that would be the method belonging to the type. So it has to be the method 12, assuming that there's only 11 methods in this. By the way, it's 1 based, not 0 based, because 0 is nil and null. So okay, that's simple again, but basically, the method list will be like the number of methods plus 1, the max plus 1. Now what happens if there's exactly 64K minus 1 methods? And the last type happens to have no methods. Then you have to store there 64K, which 2 bytes is not enough. What do we do with that? Or first, because what do we do with that? Let's look actually on confirmation that this is these are excerpts from the ECMA spec. The first one basically says that, hey, you use either 2 bytes or 4 bytes, and the decision is if there's less than, not less or equal, there's less than 2 to 16 rows. The second part says that, hey, the value which is allowed is between 1 and row count, whatever you reference, plus 1. So it doesn't say row count only, it says plus 1. And it doesn't allow 0, by the way. So how do you fix it? Well, the thing is that given that it happens only once in 17 years, because it took 17 years for actually WinRT, some WinRT type from Windows to hit this, come to us. You don't, basically, because once in 17 years, let's wait for the next one. Let's tell them to put something there. But obviously, we try to kind of do something about that. So it's not that simple. We try to kind of compensate for it, and there's like various ways how we could fix it, and there's reasons why neither of them is good. So what we could do, we could, for example, rearrange the methods and things when this kind of situation exists. Now imagine you're a developer, you compile your program, you add type. And you have maybe something that kind of does a reflection of your things, and suddenly it's different order. You might not care, but many tools do, and many developers do. So that's kind of nasty, kind of changing something sometimes for developers, from the order that compiler kind of puts out. The other thing, actually, we kind of thought about it. Hey, what if we emit? If it again happens that the last thing is the one that has no methods, or the same thing actually can appear with fields and with parameters for methods and whatnot, a couple of cases, let's emit something fake. Well, again, how would you feel if we, on your behalf, sometimes injected fake type? Many people, again, would, call it pretty nasty and would probably beat us with a stick or something. So the other thing that we considered, like, hey, I need to put there the 64K value, so let's just overflow and let's just use the 0. And that's kind of reasonable, because the 0 is not used for anything else, honestly, or not, at least not in this table. The thing is that if you look at that, it would break the ecosystem, because there's so many readers and writers and compilers and Visual Studio, and Mono has its own, and probably JetBrains have their own, and all those tools, profilers, debuggers that read directly metadata, and there's really plenty of those readers, would have to go and update their stuff, because they would not understand the 0. They would not get that, hey, suddenly basically they would feel like this is invalid. I'm supposed to, in the list, to be larger and larger number, and suddenly it's 0. What the heck, right? So that's not something we could really pull off, and in the combination of hey, it happens really once in 17 years, maybe it's fine to just live with that bug and not fix it. That was actually a little bit eye-opening. By the way, this story is 1 year old, I believe, so it's not anything ancient. So that's why it took, told you 17 years, so I should have started with that. The funny part of that, it has one more lesson learned only for me, and that's I'm not owning metadata for last 8 years or something. I'm not in the space. Guess where it landed, on whose plate, right? Once you touch a code, you own it forever. Now, luckily Michal, who kind of owns it now, he kind of did the digging, and he came is like, hey, this is kind of weird. I think it's this bug actually in the spec. Yep, it is, and it's extremely hard to fix. Anyway, spec bugs, extremely hard. Not everything has to be fixed. And that kind of brings, the kind of solutions I kind of hinted at, as I mentioned, if we would change the spec and update it, we would basically break, we would introduce a breaking change. And tools would have to adapt. It would take maybe another 5 or 10 years, and then in next 7, one person would be happy. Lots of cost, for nothing. So I'm gonna talk a little bit about breaking changes, kind of intro into that. And one thing I observed over time, and you probably that everyone, if you find a bug, especially in .NET Framework, you're happy. I found you. Just the same thing, I found a hardware, right? Issue. I was happy. So you find a bug somewhere, and the first thing you're go fix it. And how do you find it? You just don't, browse the source code. Most of you at least, to find oh, could I find some bug somewhere? Mostly it's your application fails, or actually your customers have a problem. Then you go dig, you waste 1 week or maybe more, and then you finally find out that collections throw some weird exception in some case or something. The first thing that the natural developer's reaction is this is a bug, you have to fix it. Now interestingly, there's another angle especially with .NET Framework, nobody wants to get broken. Now, when we kind of push updates and your application suddenly breaks because we changed something, and there's lots of great stories on that. The first thing you're gonna say, like, how could you change it? How could you break me? Or break not only me but my customers. Like, that's a huge impact, right? You want to avoid that. And the observation is from actually one of our architects, who's really brilliant and amazing, Jan Kotas, is that like even his changes, no matter how many people review them, no matter how many code reviews, no matter how much time you spend on that, 10% of fixes have unintended side effects, period. Now, the unintended side effects can be, hey, nothing happens, the once in 17 years bug, who the hell cares, right? Or they can be pretty significant and they can break people. We had actually extreme case, which I loved. We improved performance of something, of some loading, in time space, and it broke customers, and they were mad. Actually, at the end of the day, it was their own fault because they depended on order of loading, and we made something faster. So they used to kind of look at something, some value, and suddenly it was uninitialized because it was fast, or the other way, no, it was initialized, and they were used to the uninitialized version or whatever, right? We just made things faster, and it was the moment when you tell to the customer like, yeah, you kind of broke you, but it's kind of okay because if you don't allow us to make things faster. What else can we do actually in the code? You cannot do anything, right? However, the key things in breaking changes is that, at least how we look at that in .NET Framework, even .NET Core everywhere, is like how many customers does it break? Because if it breaks half of the world, or even like just 10% or 1%, because the numbers are super large, it's, I would probably just roll back the fix back. But if it's one customer and it's kind of their fault, sorry, you gotta change your code. Sorry. So the lesson learned, at least like from this, the key takeaway is that like, everything has a chance to break someone, including you make something faster and it can break something. And there are more stories about that. Story about, for example, finance application crashing, and it was last build of Windows 8, which was the time when we kind of roll out on ARM, the Surface RT. You know it, you remember it, you probably have it at home, use it daily or something like that. Interestingly, on the last build, what happened, that there was like latent bug or long existing bug from months ago. And the last build literally triggered it. And the triggers were two. One was that you had to have a method, engine. Engine is, when you kind of pre-compile basically your application so that you don't have to JIT at runtime. That specific, not specific method, but if a method was exactly on the 8 kilobyte page breakage on that, and if GC happened for that method twice, which means that it has to be lots of pressure, you get your method on the call stack, it had to take long time, and in the meantime GC kind of turned twice and you didn't move on from that method. If that happened, then this bug was exposed. What happened actually in that case was that there was a totally unrelated change somewhere out there. We just moved this poor method, default proxy section internal, exactly on the boundary of the 8 kilobytes. And the get default proxy thingy kind of like just takes a long time. And if you have a startup of the application, you probably allocate like crazy, and then you deallocate and things. So GC kind of, at least the Gen 0 goes over and over. And it was just exactly the same thing, great thing. It was just waiting for somebody to push it over the boundaries of 8 kilobyte and let it break. That's an example where anything can, has a risk of change. Because I bet the people who kind of edit a couple of things, there was something simple. It's like, oh, this is just one line change. You look at the code, right? It's obviously wrong. You just add this one line, everything nice. It cannot break anything, except sometimes it can. There's actually, when I talk about this with our manager, Dan, he told me actually a story which I wasn't part of, that they had one case when even just rebuild, no code change, just rebuild, broke something. because like suddenly different values and things, and something read the timestamp or whatnot and wasn't used to, I don't know, even numbers or something, and it just happened it was like the right number that kind of collided and things. So again, like that kind of brings you into this paranoia that you should not change anything. That's not good as well, right? You know, so you have to find the balance, and what usually happens that the closer you're to shipping, the more picky you are, and if someone tells you, but this is safe, you know, even then you have to say, and that's what we're saying to customers sometimes on GitHub, you see it quite often, we tell them like, yeah, it's super safe, but you know what, we're so close to shipping, it's not worth it. Like, unless it has business justification, unless it has some huge value, it's not worth the risk, just not. People have, without these experiences, have often hard time to kind of understand that, but such is life. So, what else can happen with breaking changes? And this is a fun one. This is an old one. Once upon a time, there was a text software in a certain country, and we had a huge breakage on that. We broke it. That happens. One application break it. Like not that we do it on the purpose, but honestly, with every patch we break someone. Period. It's, you know, as soon as we have 10 changes out, one of them, the 10%, is gonna break someone by accident, right? The text software, we broke printing of text forms. That's kind of bad. And we broke it exactly before the deadline of the texts. And that's a really bad combination. So the funny part on that was that the printing was tested both by Microsoft and by the company doing the text software, except we tested only printing into PDF, because who would test and like have printer next to your servers and there's like, yeah, I'm here, I can print, you don't do that. We were lucky enough to really break just that specific thing, that it broke only printing on the printer and at the wrong time, in the wrong application, and the impact sometimes can be extremely huge. So what was key takeaway from the team for us? Like, we have to be cautious around certain dates. Now, when you look at that, like some online shops and other large companies, unnamed, right? I have friends there, and they tell me like it's November, right? And they say like, oh, yep, I'm down for 1.5 months. Like, what do you mean? Well, I cannot change anything. I cannot roll out any changes because the risk of breaking that, is so huge, and we would kill the December, and December when we get like basically 30% of all our income. And small shops around here in Europe will be basically the same. So they already kind of like these kind of online shops are used to this stuff, that they basically freeze the code base, and no matter how important it is or how important you as dev think, like unless everything is on fire, you're not gonna touch the code, just to kind of de-risk and like avoid any risk. And the interesting thing from that is that actually you wouldn't think that like things like Windows or .NET Framework or something like that needs that, but yep, there are cases actually when we need to kind of have the same very similar mindset, which is kind of fun. All right, this is last story that I have, and it's a long one, but it's fun. So it's a security issue. This one is actually 1 year old, so it's pretty recent. This is from last July. Actually, it's was it like 6th July? So I think that it's almost like 1 year and 2 days old or something like that. So it started a little bit earlier, but it ran out until July. So the January before that, so it's 1.5 years ago, there was a researcher who ran some kind of ML models on Cosmos DB, which is back then wasn't public, and now it's public. And here and there, the results he got were wrong. Like they were just not matching what he kind of asked for. So we told him like, yeah, you have workaround, like just run everything twice and see if it's the same. And if it's the same, then you're good. It took them a while to kind of figure out like, hey, something is fishy probably in networking stack. I own networking, I didn't mention that, right? So that's why I kind of got into that. So that was a little bit weird, and it took us like 2-3 months to kind of work with them, because obviously everyone kind of, the first thing you go and blame like is like, hey, something underneath me, right? It's not my fault, it's somebody, under me, like, kernel. It's kernel fault, a kernel bug, You don't start that usually. But many people say like, oh, there's something fishy, you have GC, you have networking, you have this framework, it must be your fault. So the first thing was like, okay, calm down, is it, if the results are not going back as they should, like, did you check, is it problem on client side or server side? So we went through them, we kind of collected Wireshark traces, and eventually we pinned it down to actually that it's actually on client side. It took like 2 months because collecting Wireshark traces and these things actually in production, when it happens once in a while, like he didn't hit it all the time, right, is actually quite fun. I mean, it's costly, and people don't want to do that for obvious reasons. So sometimes around February, we kind of got some, stacks, or we got confirmation that it's actually on the client side. So it was like either us or Windows underneath us. So again, like, we're not evil. We're not gonna say, oh, Windows, it's your fault. We're still in the middle. We're kind of top on the stack that is kind of suspicious. So okay, let's look at that. So we look at the code, and there were some kind of buffers which were a little bit suspicious. So, but we couldn't kind of from the existing logs actually get anything useful. So what we did, we added more logging. We created custom builds of .NET Framework. We gave them to Cosmos DB, and then we waited. That was February, and in March they pinged them like, hey, so guys, like it's 1 month. So what happened? And like, yep, we lost the repro. Like, what do you mean you lost the repro? Well. Before it was filing at least once a week, and now we kind of upgraded to slightly different hardware, different data center, and the thing doesn't reproduce anymore. Like, okay, well, at that moment you cannot do anything, right? You just got the hunch that something might be wrong. You have no clues, but if you have no repro, if you have no way how to collect additional data, you're basically lost. So we waited, and then in May, another similar report kind of came. Again, like saying like, hey, the problem was basically that, you send a request and you get some weird results that don't, belong to that request. And somebody came, it was like, I think end of, mid-June or something like that, or actually, sorry, it was like end of May. And then suddenly in 2 weeks, it blew up really badly because we got like 3 or 4 teams basically on us, like with very similar symptoms. So that's when you say like, does it happen on one machine, right? That you rule that out. So we rule it out, like even multiple applications kind of cause that, which is another thing. Like you could still suspicious, like maybe they're doing something special. Maybe they're doing kind of interop that's hacking things around by accident, right? Well, if it's multiple applications having the same symptoms, it's kind of you probably, or underneath you, one of those things. So it was so many people impacted that it was all hands on the deck. And but what happened, actually the fun part was that one of the emails that came was like, I didn't realize probably for a week or 2 weeks that I'm talking to 2 teams, because the 2 teams kind of found each other, I don't know how, and they realized they have similar things. They started hacking on that, and then they come to use through the customer support or whatever. It was internal teams. And then they're like, when we started talking, like, okay, you have a repro, and they had a repro, which was awesome. And they work on that, and as long as they ask each other weird questions, like, you're one team, right? Like, no, we're 2. Like, okay, thank you for telling me right away, that helped. But anyway, they had a great repro. They had like something that failed in 20 minutes, which is awesome. And then when they played with kind of some settings, they put it down to 1 minute, which is amazing. And it was like small, like 2 pages of code, or nothing super deep. On top of that, they got the time travel TTD trace, the time travel debugging trace, which used to be called IDNA or time travel, which is, by the way, bonus. It's awesome. It's an amazing thing. So who have seen or heard about time travel debugging over here? All right. Wow, lots of people. You dealt with interesting stuff. So for the people who didn't know what it is, basically think about it. It's something that records your execution of your program instruction by instruction. So it tracks like which memory you changed, what happened, everything. So you get a trace. By the way, it slows down the execution of the program probably 10 times, which means that if you have stress bug or something like timing sensitive, often it does not reproduce with time travel trace. But if it does, you have everything, and I mean everything. Because what you can do, you can set breakpoints. You can set data breakpoints on read or write, whatever. Like, who touched this memory? You can set the breakpoint, and then you're somewhere at the crash at the end, and you say, go back, and it executes back and tells you, boom, over here. Here's the breakpoint. These are the people who wrote the data here. Okay, why did you write it here? And you can kind of basically go back, step back. Imagine the power. Like you normally go over, then you lazy to do the F11, like step into, you do F10, oops, it's the thing. So you have to restart it, and if it's like complicated repo, like over here, you do the F10, like, oh, okay, let me go back. and it's something like F10 minus. It's in WinDBG only, sorry, so it's kind of expert, but it's freaking amazing. If you have something really hard, really cool, really deep, this is a lifesaver. Anyway, I'll stop doing the pitch for this thingy because it's awesome. And the fun part was that with that we actually analyzed and root caused the problem to HTTP pipelining under stress. The bug existed for 13 years. It was there since .NET 2.0, and out of the blue, it started breaking customers. So, who knows what's HTTP pipelining? Oh, okay, that's what I kind of expected. So, I'm gonna explain it a little bit. Normal HTTP works that you have a request, you send it to the server, and the response comes back. If you want to send another request, you have to wait for the response and then send another request. And then you get another response back. What's the problem? The problem is that basically you're waiting on the ping there and going back, and of course the server time, and that's the time when you're basically not utilizing the network or anything. You're basically wasting time. So pipelining is about that you're gonna send 2 requests, and the server guarantees that it's gonna send the responses in the same order, which is, fairly duh. Why would not? And it works fairly well. So basically, as soon as the server processes the response 1, it doesn't have to wait for the client to send again, to response to arrive and send it again. It already can read the request 2 from the pipeline, and it can immediately send response 2. So it's a performance feature. Awesome. What could go wrong? Well, it turns out that it goes wrong in certain specific situation that we have at least 3 requests in the pipeline that are kind of in flight, not answered yet. And you start canceling the request. If you cancel the first one, what will you do? And the cancellation is, for example, timeout or something like that, because it's a stress, like, too many things happened, the thread was starved or whatnot, didn't get in time, boom. So if it's the first one, you just kill the connection, because the connection is useless. You're not waiting on the response 1. The response 1 might be like 10 megabytes or 100 megabytes, you don't know. Let's just kill it and re-queue the requests 2 and 3 on somewhere else, unless they were post, but let's not go into that. What is if it's the last one? Then again, solution is simple. You wait for the response 1, then you wait for the response 2, and then you're gonna kill the connection, because you don't want the wait for the response 3. Because you kind of remove that one from the queue. Now, the problematic part was if you canceled or removed something in the middle. So the code, the buggy code, was that it just removed the request from the queue. And what happened is that we got response 1, then we got response 2, and we associated it with the wrong request 3. Suddenly, that's kind of bad. Why? Because you sent request 3, and you get response to something else. So imagine you're an unnamed service, and you say something like, hey, is this data saved? Yes. Oops, that was not answer to my request. Maybe the answer was no. Or imagine you have multi-tenant service, which means that you serve multiple customers. And the request 3 is like, oh, give me data for customer A. And you get, here's data for customer B. And you show it to customer A. They will freak out. They did. They were not happy. They were asking us, are we hacked? Like, don't worry, it's just a bug. Nobody hacked you, but that's why I was like all hands on deck, because the impact was really huge. So we had a workaround. There was luckily somebody introduced the HTTP pipelining. They created some switch somewhere in the registry or whatnot that you could disable pipelining. So the perf was worse, but it worked. And we verified the fix. In parallel, we worked on proper fix. We verified it. We ran the repro. Oopsie! 4 hours in, it crashes. So first thing is like, oh, did I really put there the right bits? Does it really have the fix? It did. Actually, I think it happened even with the workaround disabled. And then we realized that there's actually the same symptoms, but probably another bug. To make things worse, the repro was extremely sensitive to actually the network, the cloud network load. So basically, whenever, so I was lucky, call me lucky. My family was already in Europe, so I was home alone. I could work 24/7, and this was fun. So I kind of did my management part of like telling the partners like, wait, we're working on it. I kind of worked with my team who's gonna work on what, and then overnight I could go and dig dive into the code because our only expert was unfortunately on vacation. He couldn't cancel because whatever reasons. So I had fun, and I felt like imposter and stupid person because whenever I finally in the evening had time to kind of debug that, I couldn't repro the thing. And it was because eventually after weeks we found out that the repro was really sensitive and it reproduced more when even 1 in 4 hours when it was actually throughout the day because the network in the cloud in Azure was against Azure, against I think storage kind of we used as one of the examples, and it just couldn't repro. So that was tough. On top of that, we tried to collect the time travel trace, so to have everything, and we failed. That kind of sucks. So we went back to kind of our original suspicion, if you remember from January, right? So half a year ago, about the buffers. So we remembered our logging. We kind of added a couple of more loggings, and yeah, we used it. And what we found out that there was indeed, from specific logs, there was actually bad buffer lifetime management. And it was on sending side. So the HTTP pipelining was we mixed it up on the receiving side, basically. This one was like we basically sent a request, but before it went to the wire, we reused the same buffer for another request. It overrode the first one, and then it was sent on the wire. So we even sent wrong things. So what was funny, that actually there was one service that kind of touched 2 other servers, and sometimes they saw requests which belonged to one server on the other server. I was like, what is it doing here? Well, because we mixed up the buffers. Kind of nasty. It was 5 years old bug, and now Karma exists, by the way. That was introduced by under my supervision of that team, of performance team and reliability team. So it was a performance feature, and we didn't do it right. So I could have stopped it if I knew. Now we tried to find out okay, what triggered this, right? Because it's 4.5.2, it's quite rare. Why suddenly? And we had Skype team who were amazing. If you ever heard this, I don't test, and when I do it in production. This is what we did. We had Skype team. We basically gave them private bits. They ran it. They were able to deploy it to one of their data center, run it for 24 hours, and they told us, is it wrong or bad? So we were basically in the 4.5.2 because we knew that 4.5.1 is okay. We kind of were doing almost binary search. Well, it was not that bad. We already had hunch, but we did a couple of builds. And it was amazing that we had kind of this service or somebody who could tell us even yes, no, does it still repro or not? Because obviously in just running the repro on your site in 4 hours or when it's extremely sensitive, we didn't have that level of confirmation. So that was amazing. If you have a team like that or something like that, that's just awesome. And by the way, that didn't mean that they intentionally broke their customers. For them, it was like, yeah, you know what, we have retries. So if something fails, we throw it away, and it's just gonna take 1 second or 100 milliseconds longer. That's fine. So that was great. And we tracked it down actually to a change in. I said 4.5.1. That was stupid. It was actually they upgraded from 4.5.2, I believe, or from something to 4.7.1. It was change in 4.7.1 that triggered this this bug. And what was funny, that actually it was basically partial fix. So imagine there was a method, and the lifetime of buffers was mismanaged. Basically, the buffer was used at the end, and it should not be. The fix that triggered this suddenly to happen, we basically started releasing it or giving it back and not using it earlier. Which when you look at that code, it was but that should kind of decrease the chance that something is gonna hit. Nope. It was suddenly, the window opportunity was smaller, yet somehow it triggered the bug. A little bit counterintuitive, but such is life. To make things better and funny, we looked at the code review and we looked on the receiving side of these buffers, which were different code, different use of buffers because the code is super complicated in networking. And we found out actually there is a bug which could have exactly the same symptoms of on the receiving side as well, rewriting buffers, as in the HTTP pipelining. We couldn't hit it with our small repro, but we don't have basically any proof that any of the customers didn't hit it. So we just fixed them. So the question is, why so many customers, hit these, three bugs basically. Two are kind of similar, but independent bugs at the same time and at once. And the only thing that we could come up with is basically, hey, maybe the Spectre and Meltdown, which actually on that January were kind of rolled out everywhere in Windows. They changed timing and things, so that could be one of the reasons, or honestly just magic. And I became a believer after this. So magic is real. And the lesson learned from that is that sometimes there are just like weird coincidences. Like one 13-year-old bug, 2 to 5 years old bug on the same day basically, or something like that, just happens to break everyone. Why? I don't know. So be ready for anything. All right, I'm gonna wrap it up, 45 minutes in. So I'm gonna recap quickly the lessons learned. So what we learned is that, always ask, does it repro on my machine? Because you don't want to debug hardware bugs. Extremely costly. Some bugs, when they are extremely rare, like just don't fix them, it's okay. People can suffer sometimes a little bit. The spec bugs are actually extremely hard to fix. You learned that probably at school and everywhere, that the sooner in the life cycle you have a bug, the harder it is fixed. So that was example like, yep, if you fix the bug, if you fix the spec, you're gonna have to fix the whole ecosystem. It's just like too costly, it's not worth it. In the combo that happens 1 in 17 years. Then anything has a risk of breaking change. Like if you remember the innocent latent bugs, that the 8 kilobyte moving thing, that something moves your code somewhere, it breaks, or just rebuild without any code change, breaks things. And the impact can be really huge. If you break text software during text season, it ain't good. Like they will not be happy. And one thing actually, if I want you to come out with some kind of outcome from this, is if you saw through the talk that like when you have a repro or something, it's just like a lifesaver. It's awesome. On top of that, if you can, you make your life easier, everyone's life easier. If you have like time travel tracing on top of it, it's amazing. And the people, for example, in networking, like they really spend time, hours and hours, probably days, to kind of from their large application to distill this small repro because they had a hunch. And you will see it on GitHub. Oftentimes people, well, not oftentimes, sometimes people come like, hey, my application is broken. It's your fault. Like, okay, do you have a small repo? I don't have time to do the small repo. I do. Because obviously, oftentimes it's actually a problem in the application itself or in higher levels. And it's like saying like, hey, my application doesn't show something in the UI. It might be Windows kernel bug, because what else, right? Kernel is involved. So let's call the kernel team. By the way, lots of people do that. Don't be those people, please. So spending time on repo is really awesome, and yeah, sometimes there's just magic, such as life. So that's it. Thank you very much. I would like to ask you for feedback. Reminder: there's gonna be survey after this. All these talks, not only for my talk but for other talks as well. DM me, email me in person after this or during the talk, what you like, what you didn't, what you would do better, whatever. I will be very, very happy. And other speakers will be happy as well. So thank you very much.